Good afternoon. I am Daniela De Luca, PhD student at the Biorobotics Institute and Department of Excellence in Robotics and AI of Sant'Anna School of Advanced Studies in Pisa. I do research in the field of visual prosthetics, and in this context, I will talk about the deployment of an instant segmentation algorithm that would allow visual prosthesis users to detect people and be able to implement social distancing. The targets of this study are, of course, the blind people. Indeed, according to the last report on vision provided by the World Health Organization, at least 2.2 billion people over the world suffer from visual impairments. Of these, 39 million are completely blind. Blindness does not only affect everything that is strictly vision related, but also many aspects of daily life. It has negative impact in terms of job and career opportunities, as well as the overall quality of life, and is associated with a higher risk of accidents, depression, falls, injuries, and social issues. Moreover, children might be affected in terms of social, emotional, and educational growth, and in the elderly, vision loss can lead to increased dependence on families or other caregivers. The COVID-19 pandemic outbreak in 2020 was a worsening factor to the lab condition. Many strategies have been developed to prevent the spread of the virus, but they are difficult for blind people to implement, so that they are more likely to contract the virus with respect to normally sighted people. Simple precautions as social distancing or hand sanitizing are not easy for them for obvious reasons, and also the access to information about the disease is more complicated. Visually impaired individuals strongly rely on touch and contact to acquire information about the surrounding environment, to safely navigate and perform daily life tasks, and consequently, the need to avoid contact with things and people results in a significant challenge. A possible solution might be using gloves, but the tactile information is limited in this case. Lockdowns and social limitation make it difficult to get assistance and support by other people, such as family or carers in the everyday life. Access to social and sanitary care for the blind has also been affected by the pandemic. Because the blind rely on light perception to maintain circadian rhythm, many of them were affected by sleep disorders. Among the preventative measures, social distancing has proven to be the most effective against the virus. However, it is hard to actuate without visual information, and blind and visually impaired people are likely to accidentally violate this rule. For example, just being in proximity of other pedestrians, especially in crowded places. Furthermore, in certain occasions, they need to ask for help, for example, to cross the street. This is clearly very poorly recommended during a pandemic. Using the long white cane might be a possible strategy to maintain social distancing, but such a tool can only provide information about the distance between the cane sensor and the surrounding objects, without giving semantic information about their nature. Moreover, one should rotate the cane of 360 degrees to get a sort of bubble of protection, but this is highly impractical. This problem might be faced through the use of visual prostheses that, in many cases, are the only way to partially recover sight when other therapies don't work. These systems are composed of different units. There is a portable external one with the aim of acquiring images and providing power supply, when usually the image is acquired with a portable camera that can be integrated, for example, into a pair of glasses and transferred to the second unit of the system, namely the image processing unit. This has the goal of selecting and extracting the useful information that has to be conveyed to the user. Once this is done, the information is typically transmitted to the user through electrical stimulation. A microelectrode is positioned at a certain level of the visual pathways, depending on where is the damage, lesion, or disease that caused vision loss. It can be implanted in the retina, and there are three possible configurations in this case, namely subretinal, epiretinal, and suprachoroidal. So far, the only type of prosthesis that has been put on the market is the retinal, with Argus 2 and alpha IMS. Other locations are the optic nerve, which could be very useful in cases when the patient cannot be considered for retinal implants due to some exclusion criteria, such as retinal detachment or strabism, because it bypasses the retina completely. Other locations are the lateral geniculate nucleus and the cortical, on which research is also focusing. However, visual prostheses have several limitations that do not allow the users to reach a proper visual acuity that remains still far from normal vision. First of all, few phosphenes are elicited because of the limitations in the dimensions of the electrode arrays and the number of electrodes. This reduced number of phosphenes elicits visual percepts of very low resolution and in a very restricted portion of the visual field. Furthermore, phosphenes are subject to a certain distortion, so that their shape is irregular and they also tend to fade in time. Finally, it is still not possible to control color perception, but only brightness. And also in this case, the obtainable grayscale is quite restricted. As a result, visual prosthesis users struggle with tasks such as objects and people detection, recognition, and localization, but also other tasks, as navigation in unfamiliar environments, for example. A possible solution, apart from adding more electrodes, is performing image processing to select the useful information from an image and finding the right way to convey to the user so as to optimize the quality of prosthetic vision. So this is the point where this work stands. The overall goal of this work is to develop an image processing algorithm to elaborate the images captured by a camera before they are fed to the stimulator. What we want to achieve is an efficient detection of instances, in particular people, their segmentation, and their localization in terms of distance from the user. To do this, we exploit RGBD cameras, which are cameras integrated with a depth sensor and deep learning algorithms to perform semantic segmentation of RGB images. Image processing for visual prosthesis has been studied by several research groups, and the several techniques have been explored. In particular, we can consider two subgroups that are different from one another, since the first one relies on the features of the images to extract the most significant part of the picture, and the other one is learning-based. But let's stick to the first one for the moment. One of the first studies was focused on experiments in which low-resolution images were delivered to normally sighted subjects to explore how images should be processed to enhance visual information content. They analyzed the grayscale effect, the spatial resolution, distance, edge enhancement. And in the end, they reported it would be better to extract some regions of interest and to deliver them to the user with reduced resolution. Later, another study proposed an image processing method that considered the edges of some objects and pixelated the images, with the ultimate goal of finding the minimum number of pixels needed to elicit a visually significant perception. On the other hand, another study from Parik co-workers focused on navigation and presented a saliency-based queuing algorithm based on, again, on intensity, saturation, edge information. Wang focused on pixelization as well and compared direct pixelization of the picture, that here is the upper right image, to two different algorithms that were saliency-based and enhanced the principal object with respect to the background. Finally, Two other studies then looked at ways to achieve adequate pixelization of the images. The first one developed two saliency-based algorithms, one that only extracts the main object of the picture, and the other that also includes the background. Similarly, the second one from Lee proposed two methods in which, respectively, the background is shrunk before pixelization or is normally pixelated but separately from the main objects after proper foreground extraction. Concerning the other group of techniques, they are learning-based approaches. Thus, they rely on the content and semantic meaning of the images. Among these, Horn and co-workers were the first to introduce its application, using semantic categories to label each pixel and enhance contrasts in the original image. Generally speaking, semantic segmentation has been extensively applied in systems for autonomous navigation of vehicles, but since it has proven particularly effective, its use has also been deployed for visual prosthetics, and unsurprisingly, several studies are focused on navigation. So, following this lead, Martinez developed an obstacle avoidance system adapting a pixel-based method initially designed for the automotive industry. The system designed by Meta instead aims to identify the pathway that minimizes collisions with people and obstacles. So it detects pedestrians, cars, and other objects that could obstruct the user's path and uses this information to calculate and provide the best direction to follow. Another one of the studies on navigation is the one from Young. They focused on metropolitan areas, applying semantic segmentation to detect traversal areas, sidewalks, stairs, water hazards, obstacles, pedestrians, vehicles, and also curbs in roadways and sidewalks. In 2020, Martinez approached the issues of social distancing for the blind, making use of semantic segmentation. His system was not intended for visual prostheses, but provides an acoustic feedback when the 1.5 meters distance rule is not satisfied. They perform real-time semantic segmentation to detect people using a depth camera to assess their distance from the patient. What we do here is to take images captured with an RGBD camera that provides us with an RGB image and its depth map, and feed the RGB image into Mascar CNN, which is a convolutional neural network that performs semantic segmentation. And then we use the depth map to get information about the distance of the instances in the picture and use it to obtain a semantic segmentation that encodes depth through a grayscale that depicts the closest objects as the brightest. Mascar CNN is a convolutional neural network developed in 2017 to do semantic segmentation. The first layers of Mascar CNN consist of a backbone for feature extraction and a regional proposal network aimed at proposing candidate bounding boxes called regions of interest. These boxes delineate areas of the picture that are likely to contain instances, and these candidates are then resized with a further layer called royal line, which ensures that the region of interest is aligned with the input image. After that, they are fed to the Mascar CNN heads. The heads are three, and each of them is responsible for one task. There are classification, regression, and segmentation. The classification is needed to predict the class each candidate belongs to. So basically, it identifies each instance. Regression is needed to adjust the bounding box coordinates of each candidate, so the left corner, the width, and the height. Indeed, the output provides not only the semantic segmentation, but also a bounding box surrounding the object. And finally, of course, the third head is dedicated to segmentation, to precisely delineate the contours of the object. The next step consists in taking the depth map into consideration. This has been captured with the RGB image and provides information about the distance of the object in each pixel in the picture. Regarding the dataset we employed, the depth map consists in grayscale images, where the closest objects are represented with darker tones of gray. It is used to determine the relative distance of all the instances in the picture and to assign them a color code, so as to simultaneously extract the information about the presence of objects and also their position in space. In particular, the color code is assigned in this way. The depth maps are basically arrays of values between 0 and 255. To obtain the distance of each object identified in the picture, we consider the pixels of the depth map corresponding to those included in the mask. We calculate their median value and assign it to the instance itself, so as to obtain a list of depth values, each corresponding to one instance. Subsequently, the instances are ordered from the farthest to the nearest. Thus, we obtain their relative position in space. Once this information is gathered, a color of the grayscale from the darkest to the lightest, namely white, is assigned to each mask as they get closer to the observers, so to give the idea of depth. The model we deployed, MaskRCNN, has been pre-trained on COCO dataset, which is commonly used for object detection and classification. Indeed, it comprises 1.5 million object instances and 91 object categories. It is made of images that could be easily found in everyday life, so that these objects are perfectly contextualized. The evaluation was done using two different RGBD datasets. One is the Salient person dataset, and it contains 929 high-resolution images that show people basically with different backgrounds and different life conditions, and they are all set in outdoor scenes. The depth maps in this case have no gaps or uncalculated distances and are perfectly aligned with color images. The other dataset is the RGBD scenes. In this case, the pictures have been taken in 14 different indoor scenes containing furniture and a set of common objects. There are no people in this dataset, but this still has been included in the analysis because it grants a higher variability and also allows to explore some particular situations that are likely to be found indoors. In this case, the depth maps were not always perfectly superimposable to the picture and also contained several gaps. Here are some examples of images processed with this algorithm. The first two rows are pictures taken from the Salient person dataset. So they mostly represent people and contain masks that are correctly assigned to each instance and encoding the correct relative distance between them. From the color code, it is possible to have an idea of depth in the scene and to correctly position the instances in the space. The other two rows are pictures taken from the RGBD scenes dataset, so mainly they represent furniture, other objects, and here the depth encoding segmentation is not always perfect. Indeed, we can observe some discrepancies, and for example, in the third result, the rightmost chair is pictured as the brightest, so it would be the closest to the observer, but in reality it is not. This is due to an imperfection in the depth mask, where we can see that some of the pixels are black because they are not perfectly aligned to the color picture, and they are on the border. Moreover, in both the last two examples, The table causes the occlusion of the objects that stand on top of it, because most of its pixels have less depth with respect to these objects. So, while the resolution is lowered, the relevant visual information must still be transmitted to the user. Semantic segmentation allows to identify certain instances of interest within the scene and provides a corresponding mask. In particular, people are successfully segmented, and in this way, the complexity of the image is greatly reduced while the main content is preserved. We chose to exploit RGBD imaging to add depth among the information to be conveyed, because depth is a very important aspect to consider in the context of social distancing and obstacle avoidance. We chose this strategy to highlight instances to prioritize those physically closest to the observer, as opposed to other methods that would instead rely on the saliency map of the image, extracting objects and regions of interest inspired by the human attention mechanism. The reason for our choice is the difficulty in obtaining good results using saliency detection when we want to analyze images where the objects can be misjudged as insignificant due, for example, to complex backgrounds or to bad lighting, or when it is difficult to recognize the main subject only based on its color, outline, or contrast. The limitations of this work are mainly linked to the occlusions caused by some objects, like tables, that are difficult to solve, but at least as far recognitions of people and social distancing are concerned, this is not a crucial problem. Another point which is quite critical is the possibility of having masks that do not perfectly overlap objects and depth maps that are not aligned with the color image. But in particular, this last aspect can be solved because we evaluated this algorithm on publicly available datasets. But if you take pictures with an RGBD camera, you can process the depth map in such a way that it is aligned with the image and has no gaps inside of it. Finally, our goal was to implement an algorithm to process images before feeding them to a prosthetic vision system to facilitate social distancing for blind individuals, since the information that can be transmitted by visual prostheses is of a much lower resolution than natural vision. With this work, we proposed a deep learning algorithm based on RGBD imaging to detect the presence of people and other objects along with their position in the environment. We exploited masker CNN to detect instances and recovered information about their position from a depth map recorded with an RGBD camera. Our method worked well in encoding the relative positions of the instances in absence of occlusions and overlapping objects that still remain an issue that has to be addressed. But in the future, more effort will be put to solve the issues of occlusions and also to integrate the algorithm into a visual prosthesis system after a proper validation through simulated prosthetic vision studies. So, although preliminary, this work might be a valuable starting point to develop a technology that can assist the visually impaired in implementing social distancing. Thank you very much. I am available to answer whatever question you have, and I hope you find this work interesting. Thank you again.